we had looked at various PWM techniques which are employed for single phase half bridge, then single phase full bridge, and subsequently for three phase as well. So as I told you, there is bipolar, where if I am going to have the frequency ratio to be MF, then we are going to have the number of pulses per cycle will also be MF, and we are going to eliminate all the harmonics. So all lower order harmonics until MF minus 1. If I am choosing MF to be even, then MF minus 1, until MF minus 1, all the harmonics will be eliminated. Order will be eliminated. And we will have the variation of the voltage from plus Vd to minus Vd. That's what we said. That's why we called this as bipolar, right? And we said invariably this will be used, this technique will be used only when we have two devices per phase or half bridge kind of cell, right? Per phase, or in a single phase case it is half bridge, right? We can use this same technique even in full bridge case. There is nothing wrong. That means we can always fire S1 and S4 together and S2 and S3 together in bipolar configuration. But we cannot use unipolar so easily in the full bridge, half bridge kind of configuration. So in this case, we are going to compare the triangular wave with plus Vm sin omega t and minus Vm sin omega t, which are 180 degrees shifted from each other. So triangular wave is compared with plus Vm sin omega t and minus Vm sin omega t. This plus Vm sin omega t comparison will yield pulses for S1 and S2. They are not of each other, right? S1 will be whenever Vm sin omega t happens to be greater than the triangular wave, and the other one is just the opposite. Whereas this is going to give out pulses for S3 and S4. So in the same leg which are there, S1 and S2 are there in the same leg, S3 and S4 are there in the same leg, they are not going to be definitely fired at the same time. So this generally is going to have 2 MF pulses normally per cycle, because we are essentially looking at S1 and S1 and S4 being fired by 2 different waves. So we are going to have something like a freewheeling interval. So we will have, in this particular case, the level will be plus Vd to minus Vd. Whereas here I will have plus Vd, 0 and minus Vd. All 3 will be there, right? These are the 3 levels. And we are going to normally use this in a full bridge VSI. And if I look at the harmonic elimination, I am going to have 2 MF minus 1. Until this, all harmonics are eliminated. Right? So very clearly, unipolar PWM technique is going to eliminate more amount of harmonics for the same frequency ratio as compared to the bipolar PWM technique. So I will probably require smaller filter in the case of unipolar as compared to bipolar. So in that sense, unipolar is definitely better. But if you look at the switching frequency, it will be almost similar. Because in the other case, S1 and S4 are fired together. Whereas here it is not that way. So if you look at the frequency of firing of each of the devices, it's almost the same. There is hardly any difference. Whereas because of the coinciding factor of S1 and S3 together or S2 and S4 together, I'm going to have zero voltages appearing here and there. So that essentially makes the number of pulses larger, not because of larger number of switchings. The switchings are still almost the same in bipolar and unipolar as long as I use the frequency ratio to be the same, right? So much so for recalling whatever we did in terms of bipolar and unipolar PWM techniques in the last class. We ended with the fact that we can apply this directly to three-phase inverters, and then I had just mentioned that if I am looking at three-phase inverters, I said that the line-to-line voltage RMS we get will be basically M times, I think I had written VD by 2 multiplied by root 3 by root 2, because VD by 2 times M happens to be whatever is the peak of the fundamental that I will be getting, from which I am looking at RMS value. So V line to line RMS for fundamental, of course, if I am talking about the fundamental value, RMS. This will be roughly the value of RMS fundamental that I can obtain, which means if I say that I don't want to go into overmodulation where M is greater than 1, the modulation index I don't want it to be greater than 1. If it is greater than 1, I am tending to square wave. Slowly I am going towards square wave. So the modulation index, the maximum modulation index for maintaining the PWM technique, right, for maintaining the PWM configuration, that is generally M equal to 1. I don't want to go beyond 1. Greater than M greater than 1 will indicate overmodulation. And I don't want to go into overmodulation because this will essentially reintroduce the harmonics. I wanted to eliminate the harmonics, that's why I was actually using PWM technique. If I make overmodulation, prevalent, then I'm going to essentially reintroduce the harmonics, which I don't want to do. So for M equal to 1, so this is going to be essentially about 61.2% times VD for M equal to 1. So I will not be able to really get a good amount of DC voltage as rather good amount of fundamental voltage. Although I am applying 100 volts of DC, what I get as the fundamental value will be only 61.2 volts, nothing more than that. So I am not utilizing the DC voltage very well. So this is one of the problems we face with sinusoidal PWM technique, and that is the reason I told you that we normally use 650 to 700 volts of DC link voltage if I want about 400 or 415 volts of line to line RMS. Whenever we use the motor drive, we normally tend to use the DC link voltage which is like 600 to 700 volts. So that is the reason why we never choose a device, even if it is 415 RMS, we never choose a device which is only corresponding to 600 volts or something. We generally choose a device which is 1 kilovolt or 1.2 kilovolt. We never choose a device which is corresponding to just 600 volts. We always choose a device which is having much higher voltage rating, like 1 kilovolt or 1.2 kilovolt, because each of them might be facing a voltage stress corresponding to that value. So that is the reason why we normally tend to choose devices which are of larger rating. And that's also one reason why multi-level inverters are more being used, extensively being used, especially in large capacity motor drives. Because if I'm looking at multi-level inverter, each of them may be having a VD of say 600 volts or 700 volts. So I will be able to cater to the needs of say 1 kilovolt drive or 3.3 kilovolt drive. So I don't have to really increase the rating of individual devices, which will increase the price also tremendously, and the stresses could be very, very large. And if one thing fails, I have to just essentially shut down my shop. Rather than that, at least if I have 2 or 3 stages of cascading operation, if one cascaded step is gone, I may be able to operate the motor drive at least at a lower voltage level if there is any need, something like that. So multi-level inverters are becoming more and more popular because of this particular reason as well. Many people call it as SHE PWM technique. So selective harmonic elimination essentially refers to eliminating particular harmonics. If I know that some particular harmonic is going to be dominating and that is going to cause a havoc in my system, then I may be able to eliminate those harmonics, effectively by using this particular technique. So I may not be able to really have, all the harmonics eliminated, but I can try to eliminate, for example, 5th harmonic, 7th harmonic. Generally, we don't talk about 3rd harmonic so much, because if I look at 3rd harmonic, normally it is all cophasal if I am looking at the 3-phase configuration. This we talked about when we were talking about the magnetizing current and its harmonics in transformer. So if I am talking about 3rd harmonic, I should write V3A, the 3rd harmonic. I should write this as some V3M, say sine omega t or cosine omega t. This omega t has to be 3 omega t now, because omega was fundamental frequency. If I am talking about 3rd harmonic, it will be 3 omega t. If I am talking about V3B, the B phase 3rd harmonic, it will be V3M sine of 3 times omega t minus 120. And V3C will be V3M sine of 3 times omega t plus 120. So obviously I am going to have this 360 degrees coming into picture in B phase as well as C phase, which actually makes all 3 of them cophasal because of this 360 degree that coming into picture, 3 times 120. So because of which I am going to have all 3 phases or 3-phase voltages in 3rd harmonic are cophasal. So if they are circulating a current through a star connected system, for example, then I am going to have essentially I3A plus I3B plus I3C will be a non-zero quantity. And unless I provide a path for that, I would not be able to really allow that to flow. So even if it is delta, it will just circulate within the delta. So if I am talking about a delta connected 3-phase winding, it will essentially circulate only within this because it is cophasal. It's like a mesh current. All of them are cophasal and they are equal in magnitude, so they can happily circulate round and round within that mesh itself, delta itself. So you would not see any of them in the lines. Normally in the lines you will not see the 3rd harmonic current. The lines will generally be devoid of 3rd harmonic currents, even though I may have some 3rd harmonic component in the voltage because they are cophasal. So generally when I look at it from the point of view of a motor drive which is being supplied from this delta, or if I am looking at any other line, that is if I am actually an electricity authority and I am looking at the lines, how they are carrying, what kind of currents they are carrying, they will not carry 3rd harmonic. So I would not see 3rd harmonic here, so I don't have to worry about 3rd harmonic so much as an electricity authority or utility industry, or if I am looking at even the inverter generating from third harmonic, ultimately it will not be supplied to the motor finally because the lines will not be having the third harmonic. So when we talk about selective harmonic elimination, especially in three-phase case, that's why we will never talk about third harmonic much. But if I am talking about single phase case, yes, I might have to talk about third harmonic as well. So in selective harmonic elimination, the basic principle is somewhat like this. Let us say I want to generate a waveform somewhat like this. So this is actually one pulse. Then I'm going to have one big pulse. And then again I'm going to have a small pulse. Something like this. Let us say this is my positive half cycle that I want to generate from my inverter. I want to actually switch my inverter at these particular angles. Okay. So let us say I want this waveform to have quarter wave symmetry as well as half wave symmetry. So quarter wave symmetry is, if I say this is alpha 1 and if I may call this as alpha 2, if I may call this as alpha 3, this is clearly pi by 2. So I can say if this is pi, this particular thing will be pi minus alpha 1. This will be pi minus alpha 2 and this will be pi minus alpha 3. So in which case I can very clearly say this has quarter wave symmetry. So whatever is before 90 degrees, it is exactly reflected on the other side also until 180 degrees. And similar thing has to happen in the negative half cycle as well. So I should have one pulse here, one more bigger pulse here and one more smaller pulse here. And I should be able to write this as pi plus alpha 1, pi plus alpha 2, this is pi plus alpha 3. That has to be 2 pi minus alpha 1, 2 pi minus alpha 2, 2 pi minus alpha 3. So I can say that this waveform completely has half wave symmetry as well as quarter wave symmetry. Now the problem at hand is twofold. One is I have to eliminate specific harmonics and maybe I have to get certain amount of voltage. Whatever is the voltage, maybe normally I'm going to get 60% or 70%. I want to get probably 50% only. So I might like to reduce the voltage, right? And I might like to eliminate certain harmonics. For this, how do I determine alpha 1, alpha 2, alpha 3? This is essentially the problem at hand. How am I going to determine alpha 1, alpha 2, alpha 3 such that I obtain a required value of RMS voltage at the output and also I am going to get essentially some of the harmonics, specific harmonics eliminated. So if I write actually what is the fundamental value for this? So fundamental component, because I have eliminated, essentially I have half wave symmetry as well as quarter wave symmetry, all the even harmonics will be eliminated, all the cosine components will be eliminated. So if I try to get the fundamental value, I should be fundamental peak, for example, which I may call as B1. Again, we are writing the Fourier expansion similar to n equal to 1 to infinity an cos n omega t plus bn sin n omega t. This is how this function will be represented. Right? No DC component, so I have not written any DC component here, basically. Right? So, we are going to have the fundamental value B1. Actually, if I say this is VDC, that is whatever is available from my DC supply side, that voltage is VDC, I should be able to write this as, first of all, from alpha 1 to alpha 2 VDC, right, sin omega t d omega t. Then I have to write from alpha 3 to pi by 2, right, again VDC sin omega t d omega t. and this has to be averaged over 4 by pi, because generally if it is done for the entire the cycle, then it is written as 1 by pi. If it is done for half a cycle, then it's 2 by pi. It is done for a quarter cycle, it is 4 by pi. So this is going to be the B1 value. B1 is the peak of the fundamental wave, right? According to whatever I have generated as this voltage waveform, if I try to calculate the fundamental, this will be the fundamental value. This fundamental value, I might like to have it as, say if DC voltage is 100 volts, I might like to have it as 50 volts, I might have to have it as 40 volts, I might like to have it as 60 volts, whatever. So I can choose what kind of value I want. So this is fixed at specified value of AC. This is one of the demands or one of the equations that need to be satisfied, right? So I should be able to definitely write exactly whatever is the value. So I can write 4 VDC by pi cos of alpha 1 minus cos of alpha 2, right? Plus cos of pi by 2 is 0. So I should write cos of alpha 3, right? So this is equal to whatever is the value. So let us say VAC specified, whatever, right? This is the first equation. The second equation, maybe I would like to eliminate third harmonic. If I am talking about single phase inverter, I should say third harmonic, which is B3. That will be again 4 by pi alpha 1 to alpha 2 VDC sine 3 omega t d omega t plus alpha 3 to pi by 2 VDC sine 3 omega t d omega t. Again I can expand this like what I have done here, right? Whatever I have done here, similar to that, I should be able to expand this. It will also have 3 alpha 1, 3 alpha 2 and maybe 3 alpha 3. This is what will be there, right? Then I can write fifth harmonic if I want to eliminate fifth harmonic. So I can write similarly d phi equal to 4 by pi integral alpha 1 to alpha 2 VDC sine phi omega t d omega t plus alpha 3 to pi by 2 VDC sine phi omega t d omega t. So now I have got 3 equations. If I want to make them as 0, I have to make third harmonic, this is equal to 0, and similarly this also equal to 0. So I have got essentially 3 equations, and in this case I have shown as though I have 3 unknowns, which are alpha 1, alpha 2 and alpha 3. So if I want to eliminate more number of harmonics, I might have to have more number of switchings, right? So here I have gone only with eliminating 2 harmonic contents, third harmonic and fifth harmonic, and I have specified a particular value of fundamental. So corresponding to these 3, I have got essentially 3 unknowns. So if I want to eliminate more number of harmonics, I should have more number of switchings. So please note that all these equations will have cos and sine, cosine and sine. So we will not be able to really solve for them directly like what we do for algebraic equations. So we need to use some kind of iterative techniques. Newton-Raphson method, that kind of method, whatever is your iterative technique, we have to use iterative techniques. So I hope you guys have studied Newton-Raphson method, no? You guys know Taylor expansion, right? So Taylor expansion basically says f of x naught plus h. If I want to write, I should write f of x naught plus h multiplied by f dash of x naught divided by f of x naught divided by factorial 1 and so on, right? H square by factorial 2 and so on and so forth. So if I say that this is f of x naught plus h is equal to 0 is the function, ultimately I want to solve for where I don't know what is h. I don't know what is h. Okay? So I should say, if I just take only the first order, I should say f of x naught plus h, is this here? I am not very sure. Maybe not. This is not there. So we will get that f of x naught underneath here. F dash of x naught, I hope it is correct, equal to 0. Right? So from here I should be able to solve for h. So h is whatever is the correction that I have to, attribute to the original solution I have assumed. I have assumed x naught as the solution. And if I have assumed x naught as the solution, definitely it will not satisfy directly the equation f of whatever x naught plus h equal to 0. That is the equation that has to be satisfied. So I can calculate what is f of x naught, and I will be able to calculate what is f dash of x naught as well, from which I should be able to calculate what is h. Right? So h equal to f of x naught divided by f dash of x naught minus of, right? I hope so. Yeah. So you get what is h. So this h is the correction that you are applying. So you would be able to get x1, the next iterative solution, equal to x naught plus h. That is the next iterative solution. Now this you will use again for getting what is the next iterative value of x, which is x2. x2 will be x1 plus h. The next h you calculate, and so on and so forth. So you would essentially assume initially certain values of alpha 1, alpha 2 and alpha 3. Right? I can simply assume them to be maybe 30 or the 15, 45 and 75 or something like that, arbitrarily. I can just assume those values and then slowly iterate them. Right? So I have to essentially iterate them with 3 functions. I have 3 functions here. Right? One corresponding to third harmonic, one corresponding to fifth harmonic, and one corresponding to fundamental. So this has to be solved iteratively. By solving them iteratively using Newton-Raphson method. So this is essentially this particular calculation of h using Taylor's expansion. This is generally known as Newton-Raphson method. So Newton-Raphson method is extremely useful, where you start off with one particular assumed solution and then you iteratively solve it, and between the 2 consecutive solutions, when the difference becomes less than some epsilon, then you say you have already reached the convergence. That's how we generally do the iterative solutions generally, right? So we actually will solve for alpha 1, alpha 2 and alpha 3 using iterative procedure. One thing you have to realize is that this alpha 1, alpha 2, alpha 3, because it is a long drawn process, to solve for it, it is not a very simple thing. So we will not be able to do it online. In the sense, we will not be able to do it in real time. When I really want to control my inverter, I was telling you that with analog electronic circuits, with microprocessors, with digital signal processors, I would be able to do this, but not selective harmonic elimination. You have to solve for it already, and you should have stored alpha 1, alpha 2, alpha 3 inside your computer, inside your microprocessor, inside your digital signal processor, and correspondingly generate the pulses for firing different devices. That is the only way out. So selective harmonic elimination normally is not an online procedure directly you can implement in analog electronic circuits or even digital platform. real-time implementation is difficult. So you have to pre-calculate the values and then store them. So sometimes we adopt lookup table kind of approach. If I want 80% of VD, if I want 70%, if I want 50%, and then if I want to eliminate these harmonics, these are alpha 1, alpha 2, alpha 3. We solve for it and then store it in lookup table. And then correspondingly, we try to, fire the inverter accordingly. So this is definitely not possible if I want to do it with analog electronic circuits. It's very, very difficult to implement selective harmonic elimination with analog electronic circuits. We normally do it only in digital platform with the help of lookup table approach. But nevertheless, this has one major advantage. With limited number of switchings, we will be able to eliminate specific harmonics if I want to eliminate specific harmonics. And then I can use a high pass filter eventually to actually eliminate all or bypass all the higher order harmonics. So if I want to specifically eliminate only particular order harmonic, it would be possible to use selective harmonic elimination. That is one of the major advantages. We told that in a three-phase inverter, what we get as the line-to-line voltage is only about 60%. If I want the modulation index to be 1, I don't want to go into over-modulation, but I want to utilize the DC voltage better. Is there any other way out? So there is one particular method which is being used to improve the utilization of DC voltage. If I want to really improve the utilization of the DC voltage, specifically in a three-phase inverter, if I am talking about a three-phase inverter, right? So in a three-phase inverter, what I can do is, I use normally the modulating wave to be a sinusoidal wave. Rather than using a sinusoidal wave, if I just use a sinusoidal wave like this, and then on the top of this, if I add a third harmonic. Let us say we try to look at the third harmonic. So the third harmonic is going to be somewhat like this. Right? This is how it will be. You understand? Because within half cycle I have to have 1.5 cycles. Only then we call that as third harmonic. So the summation of these two will essentially become, here I am going to have a little increased value. Right? Let me call this as V1, this as V3. So V1 plus V3 I am trying to draw. So when I add this, the pink color and the green color waveform, it will increase initially, and at this point it is going to start decreasing, something like this. And again it will increase here and somewhat like this. This is how it will be. So that is essentially the summation of V1 and V3. So if I use this as the modulating wave, right? I can afford to increase the fundamental magnitude further and further because third harmonic is pulling it down. Near the peak, the third harmonic is pulling it down. Because the third harmonic is pulling it down near the peak, I can actually make the peak higher than what I had chosen originally with modulation index equal to 1. So let us say the triangular wave peak is 100 volts. The sine wave peak also I would have chosen as 100 volts if I am talking about modulation index equal to 1. But if I am choosing the third harmonic with the peak which is corresponding to, let us say, 15 volts, 1.5, then I should be able to choose this sine wave. Rather than having 100 volts peak, it can have 115 volts peak, right? So that the third harmonic, even if it pulls it down, it will bring it down to 100 volts. So it will look as though at every point my triangular wave will have an intersection with the summation of V1 and V3. So my fundamental voltage will increase by about 15% if I am actually adding a third harmonic wave which is having about 15% of the peak magnitude of the original fundamental wave. So I would be able to enhance the fundamental wave by a certain magnitude provided I add actually to the original fundamental whatever is the new third harmonic, if I add them together and use them as the modulating wave. Please understand that whatever is my modulating wave, the output produced will essentially emulate my modulating wave. If the modulating wave is sinusoidal, I will have a sinusoidal output. If the modulating wave is rectangular, I will have a rectangular output. So here, my modulating wave is summation of fundamental and third harmonic. So what will be produced? That output will consist of third harmonic as well as fundamental. But it is a three-phase inverter. So I couldn't care less if there is third harmonic. Right? So this particular methodology essentially allows us to utilize the DC link voltage better than what we utilized in a sinusoidal PWM technique. This is essentially addition of the third harmonic component to the original sinusoid so that I can enhance the amplitude of the fundamental wave. But the presence of third harmonic will not affect the output of the inverter, especially in the three-phase case, because anyway third harmonic components are cophasal and those currents will not exist at the output. Right? So this is very, very commonly used in many of the three-phase motor drives. If I want to really enhance the output of the three-phase fundamental wave, then I can use summation of this single phase and fundamental and third harmonic together to make that as a modulating wave. Right? So this is one of the applications where we are trying to enhance the output of the inverter. Right? Yeah.
In this way, superimpose the third harmonic onto first harmonic.
Fundamental, yes.
Fundamental. So can't we do the same thing like add sixth harmonic?
You can add sixth harmonic, but sixth harmonic is even. Most of the times what we don't want to do is to enhance the even harmonic at any point in time. If you look at the power quality considerations, normally, if you look at any of the regulations that are imposed by power quality authority, they generally at least will give some amount of lenience towards odd harmonics. Even harmonics, they will take a very stringent view. No even harmonics can be present. They will say it cannot be more than 0.05%, 0.07%. So they are extremely stringent about even harmonics. That's one reason why we generally use MF, that is the frequency modulation ratio, as an integer. Because otherwise you can have something like subharmonics. What we mean by subharmonics is, for 50 Hertz, we generally expect 150 Hertz may be there, then 250 Hertz may be there, and so on and so forth. It is all integer multiple. But if I use frequency ratio of 1.27, 1.5, something like that, then I may have suddenly 50 Hertz, then suddenly 70 Hertz might appear, then some 85, 90 Hertz might appear, and it will be too difficult for us to deal with all those subharmonics. Subharmonics are those which are not integer multiples of fundamental. So that is one reason we don't generally use frequency ratios which are, and we never use a wave which is not having half wave symmetry. Generally. Because we don't want even harmonics or DC value to appear. And DC values generally are deadly for any AC machines. For transformer, for example, it can lead it into saturation completely, right? Because flux is in one direction and it's going to just keep on increasing if at all. There is nothing like defluxing that is happening. In alternating current, you are having flux developed in a particular direction and flux is developed in the opposite direction. So it is fluxing and defluxing, if you may call it. But in this particular case, if it is DC or, you are not going to essentially, you are going to allow the transformer to saturate. That is the problem. So even harmonics are generally never added. You may say ninth harmonic, but ninth harmonic magnitudes are generally much smaller. As the harmonic order increases, generally the magnitude of the harmonic content will decrease. The thumb rule is, if I have something like a square wave, if I say fundamental is 100%, generally third harmonic will be 1/3, 33%. Fifth harmonic will be about 20%. Seventh harmonic will be 1/7 and so on. That is how it is. If you actually calculate the Fourier coefficients, this is how they will be. Normally it will be for a square wave. So generally as the harmonic order increases, it's going to become less and less. But when we use sinusoidal PWM, I told you that frequency ratio, we are going to have the peaking of that particular harmonic. Yes, it will happen in sinusoidal PWM. Right? Okay. How do we actually modify the frequency and voltage simultaneously, especially when we are feeding a motor drive? If you may recall, you guys had done one experiment in induction motor where we used an inverter. That inverter was having basically voltage and frequency both were controlled. And if you may recall, we wrote actually for transformer as well as induction motor, this equation is valid. 4.44 F phi multiplied by number of turns. Right? This is the equation we normally wrote, if you may recall. So, if I want to hold flux as a constant, I have to essentially hold E by F ratio as a constant. And E I will not be able to measure because it is internal voltage. In the induction motor, whatever I apply as voltage minus the stated drop, what is coming across the air gap, that is E. So let me write this is approximately equal to V by F. So if I am talking about a 400 volts 50 hertz induction motor, right? If I am talking about a 400 volts 50 hertz induction motor, maybe its normal rotational velocity is 1500 RPM. Close to, I am not saying exactly, close to 1500 RPM, 4-pole induction motor. So if I am talking about running it at 750, close to 750 RPM, I have to apply essentially 25 hertz. And if I want to keep the flux almost as a constant, I have to apply only 200 volts, not 400 volts. Close to 200 volts, line to line. Nothing more than that. So I have to adjust the frequency and the voltage magnitude simultaneously, which means I necessarily need to have an oscillator which will actually generate maybe 25 hertz, maybe 50 hertz, whatever is the value of the frequency I want it to generate. Then the triangular wave frequency also need to be adjusted, because if I want to hold the frequency ratio as a constant, then the triangular wave frequency also needs to be adjusted, which is actually very, very difficult in analog electronic circuits. We have faced the music all the time. So I know that it's not easy to generate a triangular wave so easily at variable frequency, because you have to change smoothly. You can't say I am rotating the motor at 25 hertz, I want to jump to 50 hertz right away. That's not possible. So you have to change it smoothly, which means both the oscillators, the triangular wave oscillator as well as the sinusoidal oscillators, have to change their frequency smoothly. This can be very nicely, very easily done in digital. All you need to do is to give the numbers. You give 25 hertz, you give 50 hertz, you say this is the frequency ratio I want. It will very nicely generate all the pulses. So in digital implementation, it becomes much, much simpler. But how do I adjust the voltage magnitude? That is done by the modulation index. So if I assume that the modulation index in this particular case is 1, I would try to choose the modulation index in this particular case, amplitude modulation index, to be 0.5. So when I generate the sine wave, not only the frequency need to be adjusted, I will very clearly adjust the amplitude, peak amplitude, because I will keep the peak amplitude of the triangular wave as a constant. So once I vary the peak amplitude of the sine wave, keeping the peak amplitude of the triangular wave as a constant, I am modifying the modulation index. So if I am having the modulation index here as 1, and if I am getting 400 volts, obviously the output is proportional to the modulation index, because of which automatically I am going to have the amplitude of the output or RMS value of the output being decreased to half the original value. So I have to do multiple things simultaneously. First of all, adjust the frequency of the modulating wave, adjust the frequency of the triangular wave. If I have to do it in analog, it's not going to be easy, and adjust the amplitude, so that amplitude only of sine wave, not the triangular wave. Triangular wave, I would like to keep the amplitude as a constant. So this is how we normally do it when we really want to control a motor drive, right? So we actually are going to adjust all of them simultaneously. So if you actually look at the normal, if I say this is the speed I want, then this is the actual speed. So I will compare these two. It is like a control system. Very clearly, I will compare these two. The output, whatever I have got, this is going to decide really what is the kind of current or torque or whatever needs to be generated from the motor drive, so that the gap in the two speeds is bridged. The reference speed and the actual speed, whatever is the gap, that will be bridged. So I necessarily need to here decide what is, so this is the speed controller, maybe it can be a PI controller or whatever. The output, what is coming out of the PI controller, will decide whether I need a particular current, because 3I2 square R2 by S, for example, is your torque. So I can directly control what is the current. So this will actually give me I reference. But from here, from omega, whatever is the set value, this will set my frequency. Because if I know this is probably going to be my, synchronous speed, closest. So I can definitely decide what is the kind of frequency I will require, roughly. So this will set my frequency. From omega star, I will be able to set the frequency. And if I know frequency, because I want to keep V by F ratio as a constant, I should be able to say what is the kind of voltage that I need to generate from my inverter. That will set the modulation index. So from the frequency, I can calculate modulation index. Once these two are calculated, the frequency will go independently, modulation index will go independently to the VSI. Of course, VSI control circuit. I will have a control circuit which will generate all the firing pulses which will go to the VSI. Right? So let me probably show this as control. So from this, I will have 6 pulses coming out. Right? Now, this is essentially independent of the current. So I may not be able to control the current very nicely in this particular case. But if I want to control the current, very often what we try to do is to merge voltage control and current control together. At that point, we call that as current controlled VSI. We call that as current controlled VSI. So we might like to actually monitor the current also. In this particular case, we will not be able to monitor the current at all, because I have already given the pulses. It is going to the inverter. Inverter is generating the voltage and it is simply going to the induction motor. I might have to sense the current feedback. I have to give a feedback and then I might have to stop the firing pulses if the current is going too high. So in current control VSI, I would like to take a feedback from the motor drive or the inverter because they are connected in series. The output current of the inverter or input current to the motor drive I will monitor, and I would like to put that as one of the inner controls within the firing pulse generation circuit. So the firing pulse is generated, whether I release it or not, or it is going to continue or not, is decided by whether the current is within the threshold or whether it is beyond the threshold. Right? So apart from voltage source inverter and current source inverter, this is a third category, a voltage source inverter where there will be a current control which will be built in, and this is essentially used in many of the motor drives. VSI with no current control is not used very commonly in motor drives. UPS can use it, not really motor drives. So these are different categories of inverter. It is just a matter of detail I am mentioning because these are actually employed in the field. Direct VSI with sinusoidal PWM technique without current control is not used very commonly. With current control it is used along with motor drives. Right? Okay, so a half bridge inverter. Yeah? Yeah, if it has to go, if I have to show this not as a VSI control without current control. So I have to essentially compare this with whatever is the I actual. And I actual generally will be sensed either from this on the motor, or one more way of sensing it is, I will definitely have a rectifier here and I will have essentially a current here which is going into the inverter. I can sense that. So this has to be taken as this. Right? Now the output of this has to either block, or I can say if I have device number 1 and device number 4, if I give firing pulses to device number 1, the current of A phase is going to increase. If I give the firing pulse to device number 4, the current will start declining because it is connected to the negative. So I can switch between the two devices, 1 and 4. So this will work as an override over whatever is the PWM scheme even I am employing, because this will protect the motor drive against current increasing beyond a particular value. Right? So this has to actually override whatever your PWM technique is doing. Okay, so the problem statement goes as follows. A half bridge inverter has a DC supply voltage of 100 volts and operated at 1 kilohertz. 1 kilohertz is not switching frequency. 1 kilohertz is the output frequency itself. Okay? So it's a square wave inverter. The load is 10 ohm and 10 millihenry in series. Get the expression for load current for half a cycle in steady state. So we will have two capacitors and we are having RL load, and here is one switch and here is the other switch, and we are going to have diodes. Right? So this is 100 volts and these are two capacitors, and this is 10 ohm, this is 10 millihenry. They are asking for steady state expression, so we might have to solve for the initial condition also. That's what it is, right? So if you may recall, I think we actually drew the waveform somewhat like this. If we are going to get current, the voltage like this, so this will be 50 volts and 50 volts across the load, because the capacitor will have only half the voltage, right? And then you have to essentially show as though the current might come from the negative side and it will go like this, and then again it will go like this, and so on and so forth. This is how the current is going to be, right? So what is being asked is to get the expression for half cycle of the current. That's it, right? Okay, because it is RL load. So you can say that this is 1 kilohertz, so the period is going to be 1 millisecond, and time constant also we can get L by R, which is 10 millihenry divided by 10, so that is also 1 millisecond. Time constant of the circuit is also 1 millisecond, right? So you can calculate, basically let us write the expression in terms of, if we say VD is 50 volts. So this is VDC, which is 100 volts. Okay. So we have to write I of t during positive half cycle will be what? It will be VD divided by R into 1 minus e power minus t by tau. That is one portion, right? The other one will be whatever is the current that it is starting off with. So if I may call this as I naught. So it is going to be, and if I say this is minus I naught, this will be plus I naught. In steady state, both have to be the same. When once it reaches steady state, I should have positive peak and negative peak magnitude should be equal to each other. That's when you call it a steady state. So I should say this minus I naught into e power minus t by tau. This is what will be the expression for the current, first order differential equation solution, right? And to solve for I naught, I should be able to say that when it is at half cycle, right, I should be having again I of t to be I naught itself, right? So at t by 2, if I assume that this is 0 and this is t by 2, at t by 2, I of t is equal to I naught. So I should be able to say I naught equal to Vd divided by R into 1 minus e power minus t by 2 tau. Right? Because small t is equal to capital T by 2. Minus I naught into e power minus t by 2 tau. Right? So t and tau were exactly the same, 1 millisecond. So e power minus half, we'll have to substitute, and then we should be able to get what is the value of I naught. Once we have the value of I naught, you have the entire expression with you. 50 divided by 10, which is 5 multiplied by 1 minus e power minus t by tau. Tau is 1 millisecond, so minus 1000 t. Minus I naught value you can solve for from whatever we have written. So the expression is there. Right? Get my point? So it is essentially your circuit transient solution, nothing more than that. So this will be the expression during the positive half cycle. So this is true only once the circuit reaches steady state. So initial stage, if you have to solve initial few cycles, definitely you will see that the positive half is dominating over the negative half if it had started with the positive half cycle. Right? So you would see that the current is dominating over the negative. Right? A square wave inverter with single pulse width modulation, that is only one pulse being modulated. Okay, modulation yields rated RMS output voltage when the duty ratio, you may call that as duty ratio, that is, for example, if I am having this as the complete positive half and this as the complete negative half, if this is conducting only for 50% of the time, so I am calling that duty ratio as 0.5. So out of the total duration, how long each of the devices conduct, right? So they are supposed to conduct for 100% of the duration if it is a square wave inverter. Rather than that, I am probably making it on only for 50% of the duration. So if I say that this is essentially dt by 2, this entire thing is t by 2. Okay? So the duty ratio we define as this. So when the duty ratio D is, say, 60%. What should be D value if the output has to be enhanced to 110% of rated value? Pretty simple though. Only thing I want to emphasize is we have to take root of D, isn't it? You understand the point? Because when we are actually looking at the output, it will be RMS value. So I should say if this is VD, I should say VD square multiplied by D of T. And D of T, I have to essentially take it from 0 to dt by 2. And I have to average it over T by 2. So I will get essentially whatever is VD multiplied by root of D as the RMS value. That's what I wanted to emphasize. That's why I just took this. The same thing holds good for AC voltage controller. You remember when we did integral cycle control, we said it is root of m by m plus n. The same thing holds good here because it is going to conduct only from, let us say, 0 to dt by 2. But it has to be averaged over t by 2. And we have to say Vd square dt. And then it has to be taken as square root. This will be my VO RMS. Right? So essentially what I get will be Vd multiplied by root of D. Right? So in this case I have to simply say V rated equal to root of 0.6 multiplied by Vd. So 1.1 times V rated equal to root of D nu multiplied by Vd. So you should be able to calculate what is D nu. So space vector modulation technique, normally we have in three-phase cases, three independent quantities to be controlled. We generally say VA, VB and VC. But we also know that normally in any three-phase configuration, we will have VA of T, instantaneous voltage, VB of T and VC of T together will make up for 0 at any point in time. So, you can't say all the three are completely independent quantities. They can be definitely represented by just two quantities. There are only two independent quantities. So, normally what we try to do is to transform these three quantities into two independent quantities. And we call them as alpha and beta. We first of all transform the three-phase quantities into two independent quantities which are alpha and beta, and we generally take them as perpendicular to each other. If alpha is along a phase axis, we take beta perpendicular to it. Some books take this as leading, some books take this as lagging. I take this normally as leading because that is the way I have learnt completely my transformation. So, I generally go with the leading, beta leading over alpha. So, I will have essentially, let us say this is VA, VB, VC, and I am going to take essentially alpha along this and beta along this. Once I transform the voltages that are independent of each other or the currents which are independent of each other, which are in three phases, into alpha and beta, I should be able to write this as a complex number representation. I can always write V alpha plus J V beta is what is the overall voltage of all the three phases. So, instead of having three independent voltage quantities, I can merge them into a single vector. I call this as the space vector. So, this particular vector, which is actually combining all the three-phase quantities into a single complex quantity, we call this as the voltage space vector. It's very difficult to actually give a physical meaning for the voltage space vector, but for current we may be able to give it better. If you may recall, in induction motor, we said we had IA, IB and IC passing through space distributed winding, which gave rise to a revolving magnetic field. So, when a current is flowing through an inductive coil, we are able to at least give it a physical meaning, saying that it is actually showing a particular value of probably the flux combined together, when you actually combine all the three phase fluxes together, right? And that is showing a revolving magnetic field. That's what we said. So, essentially for voltage it is very difficult to give a physical meaning, but for current at least we would be able to say it is showing a flux vector which is visualized in a space, maybe in air gap or whatever. So, what actually the inverter control using space vector modulation does it is, if I have VA, VB, VC which are sinusoidal in nature normally, we say that at a particular situation maybe my flux vector or the current vector is this way. After some time it rotates like this. After some time it goes on rotating in anti-clockwise direction if I keep applying a three-phase quantity to a three-phase winding. So, whenever I am going to have only three switches of the inverter on, maybe it is 6, 1, 2, maybe 1, 2, 3, maybe 2, 3, 4 and so on, can we say that the voltage occupies this particular position? Maybe it occupies this particular position. Maybe it occupies this particular position. Whether can we correlate a particular situation or the on state of different switches with a particular position of the space vector? So, what actually people who had worked on space vector modulation did was to, rather than jumping from say 612 to 123 directly, can I make a movement which is slow and steady? Then it will essentially emulate exactly a sinusoidal transition. It will not jump from 612 to 123, 123 to 234 and so on. If I can do it slowly, maybe if I can get something in between states, how do I get? I'm not sure, because 612 is a discrete way of turning on 3 switches. And again, from that you can jump to 123. But how do I achieve in between the 2 states? So that is what space vector modulation technique addresses. How do I really get into anywhere in between? Because if I say discretely, this is corresponding to 612 being on, this is being 123 being on, how do I achieve any of the states in between? If I can decipher that, I would be able to make my inverter function in such a way that it generates some wave very close to a sinusoid. Right? And that is the crux of space vector modulation. So what we will do while studying about space vector modulation is, first of all, we will try to map each of the inverter states, that is whether it is 612 or 123 or 234, to a particular space vector position. Once we do that, then we would try to find out if I want to generate a voltage which is corresponding to somewhere in between, how do I do that? Really by making use of these finite states of the inverter. I have only finite states because I have only 6 switches. So using that I have only finite states of switching. So how do I really generate any voltage which will be mapped somewhere in between among these discrete states by adjusting the switching combinations? So this is what we are going to look at for space vector modulation, and this actually allows us to utilize the DC link voltage also much better. So that's why I would like to conclude the PWM with this space vector modulation.